Tonight, we're going to drift through the greatest story ever told. Not written in books or whispered through generations, but written in light itself, in the very atoms that compose everything around you. This is the story of the observable universe, from the first incomprehensible instant to the vast cosmic structures we see today. A journey that spans nearly 14 billion years, and yet somehow all of it leads here, to this moment, to you. So settle in, let your breathing slow, and let's begin where everything began. 13.8 billion years ago, give or take about 21 million years, the universe burst into existence. But calling it a burst doesn't quite capture what happened. There was no explosion in space, no expanding cloud of debris. Space itself was born in that instant, along with time, along with energy, along with every law of physics that would govern the cosmos from that moment forward. Scientists call this the Big Bang, though the name itself feels inadequate for what occurred. Picture trying to describe the entirety of human history in a single word, and you'll understand the challenge. What we know and what we've pieced together from careful observations and elegant mathematics is that the universe began in a state of almost unimaginable density and temperature. Everything that exists today, every galaxy, every star, every planet, every atom in your body was compressed into a space smaller than a single atom. Smaller than that, smaller than anything we can meaningfully visualize. The very first moment, the absolute beginning, remains hidden from us. Physicists call this earliest period the Planck epoch, named after Max Planck, the father of quantum theory. It lasted from time zero until approximately 10 to the power of negative 43 seconds after the beginning. That's a decimal point followed by 42 zeros and then a 1. An interval so brief that our minds simply slide off it like water off glass. During the Planck epoch, the universe was unimaginably hot. We're talking temperatures around 10 to the 32 power Kelvin. At these temperatures, at this density, the very concepts of space and time as we understand them break down. The four fundamental forces that govern our universe today, gravity, electromagnetism, the strong nuclear force, and the weak nuclear force, were all unified into a single force. Everything was one thing, undifferentiated, pristine. Our current theories of physics simply don't work in these conditions. General relativity, which describes gravity and the large-scale structure of space-time, and quantum mechanics, which describes the behaviour of the very small, both reach their limits here. They give conflicting answers, infinite values, mathematical nonsense. To truly understand the Planck epoch, we would need a theory of quantum gravity, a unified description of how the universe behaves when both gravity and quantum effects are equally important. String theory, loop quantum gravity, and other candidates have been proposed, but we don't yet have a complete answer. So we stand at the edge of the knowable universe, looking backward through time, and we can only see so far. Before the Planck epoch ends, before that first tiny fraction of a second passes, the universe is opaque to us. Not because light couldn't travel through it, but because the very framework we use to ask questions about what happened breaks down. But let's move forward now, into territory where our physics begins to work again. As the universe emerged from the Planck epoch, it entered what's called the Grand Unification epoch. Still incomprehensibly hot, still smaller than anything you could hold in your hand, but now describable by extensions of our current theories. The temperature had dropped, if we can use that word for something still around 10 to the 27 Kelvin, cool enough for gravity to separate from the other three fundamental forces. This separation was momentous. In our universe today, gravity is by far the weakest of the four forces. If you've ever picked up a paperclip with a magnet, you've witnessed a tiny magnet overcoming the gravitational pull of the entire Earth. But in these earliest moments, all forces had comparable strength. As gravity peeled away and became distinct, it set the stage for all the structure that would eventually form. From stars to galaxies to the very fabric of space-time itself, the universe continued expanding. As it did, it cooled further, like steam cooling into water, water cooling into ice. At around 10 to the negative 36 seconds, something remarkable happened. Something that would shape the entire future of the cosmos. The strong nuclear force separated from what remained of the unified force, now called the electroweak force. This separation triggered a phase transition, much like water freezing, and that phase transition drove the most dramatic event in cosmic history: inflation. Cosmic inflation is one of those ideas that sounds like science fiction but has become central to our understanding of the universe. The theory, proposed by physicist Alan Guth in the early 1980s, suggests that for a tiny fraction of a second, perhaps from 10 to the negative 36 seconds to 10 to the negative 32 seconds after the Big Bang, the universe underwent exponential expansion. Not just fast expansion, exponential expansion. During inflation, the universe doubled in size every tiny instant, perhaps every 10 to the negative 35 seconds. After just 100 of these doublings, a region of space no bigger than an atomic nucleus had grown larger than the visible universe we see today. By the time inflation ended, that tiny patch had expanded by a factor of at least 10 to the 26th power. Imagine a grain of sand suddenly becoming larger than the observable universe. That's the scale we're talking about. Why would the universe do this? The answer lies in a hypothetical field called the inflaton field. Like the Higgs field that gives particles mass, the inflaton field permeated all of space. In its high-energy state, it created a kind of repulsive gravity, a negative pressure that drove space to expand at this ferocious rate. As the inflaton field dropped to its lower energy state, like a ball rolling down a hill, it released enormous amounts of energy. This energy flooded the universe with particles, heating it back up in what's called reheating. The hot Big Bang, as we usually think of it, really began here at the end of inflation. Inflation solves several puzzles that had troubled cosmologists. First, there's the horizon problem. When we look at the cosmic microwave background radiation, the afterglow of the Big Bang, we see that it has almost exactly the same temperature in all directions. But according to calculations without inflation, regions on opposite sides of the sky should never have been in contact with each other. They're too far apart. Light hasn't had enough time to travel between them since the Big Bang. So how did they end up at the same temperature? Inflation solves this. Before inflation, the entire observable universe was so small that it was in thermal contact. Everything could equilibrate to the same temperature. Then inflation stretched that tiny uniform region out to cosmic scales. What we see as opposite ends of the universe today were actually next-door neighbours before inflation began. Second, there's the flatness problem. The universe appears to be geometrically flat, or very close to it. Space doesn't curve dramatically. Parallel lines stay parallel, but this flatness is unstable. As the universe evolves, any deviation from perfect flatness should get amplified. For the universe to be as flat as we observe it today, it would have had to start out extraordinarily, implausibly flat. Inflation, however, takes any curvature and smooths it out, like inflating a balloon smooths out its wrinkles. After inflation, the universe would naturally be very flat, which is exactly what we observe. Third, inflation explains the seeds of structure in the universe. The galaxies, stars, and planets we see today didn't just appear randomly. They formed from tiny density fluctuations in the early universe. But where did those fluctuations come from? Inflation provides an answer. During the inflationary epoch, quantum fluctuations, tiny random jitters at the smallest scales, were stretched to cosmic proportions. These quantum seeds, frozen into the fabric of space itself during inflation, later grew under gravity into the galaxies and large-scale structures we see today. Evidence for inflation comes from detailed observations of the cosmic microwave background. The pattern of hot and cold spots in that ancient light matches the predictions of inflation remarkably well. The fluctuations are nearly scale invariant, meaning they have similar strength at different scales, just as inflation predicts. The universe appears flat, as inflation predicts, and the different regions of the sky show the correlations we'd expect if they were once in contact before inflation separated them. As inflation ended and reheating began, the universe was filled with a hot, dense soup of fundamental particles. We've now reached about 10 to the negative 12 seconds after the Big Bang. The universe has cooled to around 10 to the 16 Kelvin, still unimaginably hot, but cool enough that we can describe what happens next with confidence. The physics here has been tested in particle accelerators on Earth. After reheating, the universe entered the quark epoch. The cosmos was filled with a seething plasma of quarks and gluons, the fundamental building blocks of protons and neutrons. Also present were leptons, including electrons and neutrinos, along with their antimatter counterparts. Photons of light streamed through this primordial soup, constantly colliding with other particles, scattering, being absorbed and re-emitted. Everything was too hot, too energetic for stable structures to form. Quarks couldn't bind together into protons and neutrons. They remained free, swimming in a sea of gluons, the particles that normally hold quarks together inside atomic nuclei. This quark-gluon plasma was the densest, hottest state of matter the universe has ever known, outside of the very first instance we've already discussed. As the universe continued to expand and cool, it reached a critical threshold at about 10 to the negative 6 seconds, or 1 microsecond after the Big Bang. The temperature had dropped to around 10 to the 13 Kelvin. This was cool enough for quarks to bind together to form composite particles. The universe underwent another phase transition, this time from quark-gluon plasma to ordinary hadronic matter. Quarks clustered in groups of 3 to form baryons, the most important of which are protons and neutrons. They also paired up in quark-antiquark combinations to form mesons, which are unstable and quickly decayed. The strong nuclear force, mediated by gluons, held these quark triplets together tightly, creating the particles that would eventually make up atomic nuclei. But there was a puzzle, one that remains one of the deep mysteries of physics. In principle, the Big Bang should have created equal amounts of matter and antimatter. Every quark should have been matched with an antiquark, every electron with a positron. And when matter meets antimatter, they annihilate, converting their mass entirely into energy, into photons. If there had been perfect symmetry, the universe should have annihilated itself completely, leaving nothing but a sea of light. Clearly that didn't happen. We exist. The universe is full of matter. So somewhere in these early moments, there must have been a slight asymmetry, a tiny preference for matter over antimatter. For every billion antiquarks, there might have been 1,000,000,001 quarks. The billion pairs annihilated, and that one extra quark survived. Multiply that by the vast number of particles in the universe, and you get all the matter we see today. The cause of this matter-antimatter asymmetry is still unknown, though physicists have proposed various mechanisms. It might be related to the behavior of certain particles under specific conditions, perhaps involving the weak nuclear force, or physics beyond the Standard Model. Whatever the cause, we owe our existence to this tiny imbalance. By 1 second after the Big Bang, the universe had cooled to about 10 to the 9 Kelvin. Most of the hadrons and antihadrons had already annihilated each other. Now the leptons and antileptons began their own annihilation, Electrons and positrons collided and disappeared in flashes of gamma rays. The neutrinos, which interact only weakly with other matter, decoupled from the rest of the universe, beginning their journey through space that continues to this day. These cosmic neutrinos form what we call the cosmic neutrino background, a sea of nearly undetectable particles that fills the universe, though we've never directly observed them because they interact so rarely with matter. Between 1 and 3 minutes after the Big Bang, the universe entered a crucial phase called Big Bang nucleosynthesis. The temperature had dropped to about 1 billion Kelvin, cool enough for atomic nuclei to hold together without being immediately torn apart by energetic photons. Protons and neutrons began fusing together to form the lightest elements. First came deuterium, or heavy hydrogen, with 1 proton and 1 neutron, then helium-3 and helium-4, tritium, and a tiny amount of lithium-7. These fusion reactions happened in the hot, dense conditions of the early universe, much as they do in the cores of stars today, but the conditions were different. The universe was expanding and cooling rapidly, which meant nucleosynthesis only had a brief window to occur. After a few minutes, the temperature had dropped too much, and fusion stopped. The result was a universe composed of about 75% hydrogen by mass and about 25% helium-4, with trace amounts of deuterium, helium-3, and lithium-7. Essentially no heavier elements formed during Big Bang nucleosynthesis. The jump from helium to carbon and beyond requires conditions that didn't exist in the early universe. It would take the formation of stars hundreds of millions of years later to create the heavier elements like carbon, oxygen, iron, and gold. The precise abundances of these light elements, hydrogen and helium especially, are one of the key pieces of evidence supporting the Big Bang theory. When we look at the oldest, most pristine gas clouds in the universe, gas that hasn't been contaminated by stellar processes, we find these exact ratios, about 1 helium nucleus for every 12 hydrogen nuclei. The agreement between prediction and observation is striking, one of the great successes of modern cosmology. For the next several 100,000 years, the universe continued expanding and cooling, but not much changed structurally. This was the photon epoch, or the radiation-dominated era. The universe was filled with photons of light, electrons, protons, helium nuclei, and the mysterious dark matter, which we'll discuss more later. Everything was still far too hot for atoms to form. Electrons couldn't attach to nuclei because the ambient energy was so high that any electron that tried to bind would immediately be knocked free by a passing photon. During this time, matter and radiation were tightly coupled. Photons constantly scattered off free electrons in a process called Thomson scattering. A photon would travel a short distance, hit an electron, scatter in a new direction, travel another short distance, scatter again, over and over. The universe was opaque to light, like trying to see through fog. Even though photons were everywhere, they couldn't travel freely. The cosmos was a brilliant, glowing plasma, but you couldn't see across it. Any observer, if one could have existed, would have seen nothing but a uniform glow in every direction. Beneath this glowing surface, though, structure was beginning to form. Tiny density fluctuations, the quantum seeds stretched out during inflation, were starting to grow under the influence of gravity. Regions that were slightly denser than average attracted more matter, becoming even denser. Regions that were slightly less dense lost matter to their neighbours, becoming voids. Dark matter played a crucial role here. Unlike ordinary matter, dark matter doesn't interact with light. It doesn't feel the pressure of photons. So while ordinary matter, the protons, neutrons and electrons, were still locked in the photon-electron plasma, unable to collapse under their own gravity because photon pressure kept pushing them apart, dark matter was already beginning to clump. It was falling into the gravitational wells created by those early density fluctuations, forming the scaffolding on which galaxies would eventually assemble. By about 10,000 years after the Big Bang, the universe had expanded enough that matter began to dominate over radiation. Before this, the energy density of the universe was mostly in the form of radiation, of photons. But as the universe expands, radiation dilutes faster than matter. Photons get redshifted, losing energy, while matter just spreads out. Eventually, matter took over as the dominant component, and from this point forward, the dynamics of the universe's expansion were controlled primarily by matter, both ordinary and dark. At around 370,000 years after the Big Bang, a milestone occurred that fundamentally changed the nature of the universe. The temperature had finally dropped below 3,000 Kelvin, cool enough for electrons to settle into stable orbits around protons and helium nuclei. This process is called recombination, though the name is a bit misleading. The electrons and nuclei weren't recombining, they were combining for the first time. As electrons attached to nuclei, forming neutral hydrogen and helium atoms, the character of the universe transformed. With free electrons now bound up in atoms, photons no longer had anything to scatter off. Suddenly the universe became transparent. Light that had been trapped, bouncing endlessly from electron to electron, was now free to travel. It streamed outward in every direction, carrying with it a snapshot of what the universe looked like at that moment. This light is still travelling through space today, stretched and cooled by the expansion of the universe. We call it the cosmic microwave background radiation, or CMB. It fills the entire universe, coming from every direction, a faint whisper from the distant past. When it was first emitted, it had a temperature of about 3,000 Kelvin, glowing in the visible and infrared parts of the spectrum. Today, after 13.8 billion years of cosmic expansion, it has cooled to just 2.7 Kelvin, above absolute zero, and it now glows primarily in microwaves. The discovery of the CMB in 1964 by Arno Penzias and Robert Wilson was one of the defining moments in modern cosmology. They detected this faint microwave hiss coming from all directions in space, uniform to 1 part in 100,000. At first they thought it might be noise from their instruments or even pigeon droppings on their antenna, but it persisted, constant and omnipresent. They had found the afterglow of creation itself. The CMB is one of the most important tools we have for studying the early universe. By measuring its temperature and polarization with exquisite precision, missions like COBE, GeoMap, and Planck have given us a baby picture of the universe, a snapshot of what the cosmos looked like when it was just 370,000 years old. The tiny temperature fluctuations in the CMB, variations of only a few millionths of a degree, map out the density fluctuations that would later grow into galaxies and galaxy clusters. They tell us about the composition of the universe, its geometry, its age, and its history. After recombination, the universe entered a period known, somewhat dramatically, as the Dark Ages. The name is apt. With recombination complete, there were no free electrons left to emit light. The CMB photons were now just travelling through space, gradually redshifting, fading. And for hundreds of millions of years, there were no stars yet to illuminate the cosmos. The universe consisted mostly of neutral hydrogen and helium gas, dark matter, and the omnipresent but invisible CMB radiation. But calling this period the Dark Ages doesn't mean nothing was happening. Far from it. Beneath the darkness, profound changes were taking place. The density fluctuations that had been growing during the radiation-dominated era continued to evolve. Dark matter, already starting to clump, was pulling ordinary matter along with it. Think of dark matter as the skeleton of the universe, invisible but providing structure. Where dark matter concentrated, it created gravitational wells, deep valleys in the landscape of space-time. Ordinary matter, the hydrogen and helium gas, began to flow into these wells, slowly at first, then faster as the wells deepened. The gas accumulated, forming dense clouds. These clouds were not uniform. They had structure, regions that were denser than others, shaped by the primordial fluctuations imprinted during inflation. As the clouds collapsed under their own gravity, they fragmented into smaller clumps. These clumps continued to collapse, heating up as gravitational potential energy converted into thermal energy. This was a slow, quiet process. For perhaps 100 million years, maybe 200 million, the universe remained dark. There were no stars, no galaxies, just clouds of gas gradually, inexorably, falling together under gravity's patient pull. The temperature of the gas, which had started at 3000 Kelvin at recombination, continued to cool as the universe expanded. By the time the first structures were forming, the gas had cooled to perhaps a few hundred Kelvin, still far above the temperature of space today, but cool enough that other processes could begin. One of the most important processes was the formation of molecular hydrogen. Most of the hydrogen in the universe exists as single atoms, one proton with one electron. But under certain conditions, two hydrogen atoms can bond together to form molecular hydrogen, H2. This molecule is crucial because it's an efficient coolant. When molecular hydrogen forms, it can radiate away energy more effectively than atomic hydrogen, allowing gas clouds to cool further and collapse more rapidly. The formation of molecular hydrogen was a delicate process in the early universe. It required a catalyst, often a free electron or a hydrogen ion, to facilitate the bonding. Once even a tiny amount of molecular hydrogen formed in a collapsing gas cloud, it would help the cloud cool, increasing its density, which in turn led to more molecular hydrogen formation. A feedback loop, positive and accelerating. As these clouds collapsed and cooled, they spun up. Conservation of angular momentum forcing them into rotating structures. Some fragmented into multiple clumps, proto-galaxies or even smaller protostellar clouds. The gas in the very centres of the deepest gravitational wells began to heat up dramatically as it fell inward. Pressure increased, density increased, temperature increased, and then after perhaps 150 to 200 million years of darkness, something extraordinary happened. In the densest cores of the most massive collapsing clouds, the temperature climbed above 10 million Kelvin. At this threshold, nuclear fusion ignited. Hydrogen atoms slammed together with enough force to overcome their electrical repulsion and fuse into helium, releasing enormous amounts of energy in the process. The first stars began to shine. The universe's first generation of stars, what astronomers call population 3 stars, were nothing like the stars we see in the sky today. They formed under conditions that would never exist again, from gas that was almost entirely hydrogen and helium, with essentially no heavier elements. This pristine composition had profound consequences for how these stars formed and what they became. Without heavier elements, the gas couldn't cool as efficiently during collapse. Elements like carbon and oxygen, even in trace amounts, act as excellent coolants because they can radiate energy away through various atomic transitions. But the first gas clouds had none of these. They could only cool through molecular hydrogen, which was less efficient. As a result, the gas in these first collapsing clouds had to be hotter and denser before it could fragment and form stars. This favoured the formation of very massive stars, perhaps tens or even hundreds of times the mass of our Sun. Theoretical models suggest that population 3 stars may have ranged from about 10 solar masses up to perhaps several hundred solar masses. though there's still significant uncertainty. These massive stars would have been incredibly luminous, burning fiercely hot, with surface temperatures around 90,000 Kelvin or more, 10 times hotter than our Sun. Their blue-white light would have been rich in ultraviolet radiation, energetic enough to ionize hydrogen atoms in the surrounding gas. Despite their brilliance, these first stars were probably quite rare. Each collapsing dark matter halo might have produced only one or a few population 3 stars before the conditions changed. And they were short-lived. Massive stars burn through their fuel rapidly, racing through their life cycles in just a few million years compared to the 10 billion year lifespan of a star like the Sun. When population 3 stars died, they died spectacularly. The most massive ones, those above about 25 solar masses, would have ended in supernova explosions, blasting their outer layers into space. These supernovae would have been among the brightest events in the early universe, briefly outshining entire proto-galaxies. The energy released would have been enormous, heating and stirring the surrounding gas, creating shock waves that propagated for thousands of light years. Crucially, these supernovae produced the first heavy elements, the first atoms of carbon, nitrogen, oxygen, silicon, iron, and all the other elements heavier than helium. These elements were forged in the cores of the stars through nuclear fusion and in the violent conditions of the supernova explosions themselves. When the shock wave from a population 3 supernova swept through a region of space, it scattered these newly created elements into the pristine hydrogen and helium gas. This process, called chemical enrichment or metal enrichment in astronomers' language, changed everything. Even a tiny amount of heavy elements, a fraction of a percent, dramatically increased the ability of gas clouds to cool during collapse. This meant that subsequent generations of stars could form at lower masses, creating a wider range of stellar types. The era of pure population 3 stars was brief, perhaps lasting only a few 100 million years, before giving way to population 2 stars, which had small but non-zero amounts of heavy elements in their composition. Some of the most massive population 3 stars, those above about 140 solar masses, may have met an even more dramatic fate. Theoretical models predict that such stars could experience a pair instability supernova, where the intense gamma radiation in the core produces electron-positron pairs, causing a catastrophic instability. The entire star explodes, leaving no remnant behind, no neutron star or black hole, just a scattered cloud of elements and energy. These explosions would have been extraordinarily powerful, perhaps 100 times more energetic than typical supernova. And then there's the question of the smallest population 3 stars and the largest. Stars much less massive than about 10 solar masses would have burned their fuel so slowly that they could still be around today, faint and red and ancient, perhaps hiding in the outer reaches of galaxies. Astronomers have searched for these relics, looking for stars with essentially zero heavy element content, but none have been definitively found. It's possible the very first stars simply didn't form below a certain mass threshold, or that we haven't looked carefully enough yet. At the other extreme, some population 3 stars might have been truly supermassive, perhaps hundreds of thousands of times the mass of the Sun. These behemoths could form in very rare, very dense gas clouds, perhaps in the centres of the most massive dark matter halos. Instead of exploding as supernova, they would have collapsed directly into black holes. Massive black holes, perhaps tens of thousands or even hundreds of thousands of solar masses. These could have been the seeds of the supermassive black holes that we find in the centres of galaxies today, including the Milky Way. The intense ultraviolet light from population 3 stars had another crucial effect. It began to reionize the universe. Remember, After recombination, the universe became neutral, filled with neutral hydrogen and helium atoms. But the energetic photons from the first stars could strip electrons away from these atoms, turning neutral hydrogen back into ionized plasma. This process, called reionization, gradually cleared the fog of neutral hydrogen, creating expanding bubbles of ionized gas around each star and proto-galaxy. At first, these bubbles were small and isolated, each one surrounding a single star or small cluster. But as more stars formed, the bubbles grew and merged, overlapping and eventually connecting. By about 1 billion years after the Big Bang, most of the hydrogen in the intergalactic medium, the space between galaxies, had been reionized. The universe became transparent to ultraviolet light, which meant that light from distant objects could travel unimpeded across the cosmos. The Dark Ages were over, but the process of forming galaxies was just beginning. Those first stars didn't exist in isolation. They formed within collapsing dark matter halos, and those halos were themselves merging and growing. Dark matter dominated the mass budget of the universe. About 85% of all matter was and is dark, invisible to telescopes, but detectable through its gravitational influence. Dark matter halos grew hierarchically, meaning smaller structures merged to form larger ones. A halo containing a few million solar masses of dark matter might host a few population 3 stars. That halo would then merge with other similar halos, growing into a structure with tens of millions of solar masses, capable of hosting dozens or hundreds of stars. These proto-galaxies continued merging, assembling over hundreds of millions of years into structures recognizable as the first true galaxies. By about 400 to 500 million years after the Big Bang, the first small galaxies had formed. These weren't grand spirals or giant ellipticals like we see in the nearby universe today. They were smaller, more irregular, often quite chaotic. They were still assembling, still accreting gas, still experiencing bursts of star formation and frequent mergers with neighbours. The James Webb Space Telescope, launched in late 2021, was specifically designed to observe these earliest galaxies, and it has delivered, finding galaxies that existed when the universe was only a few 100 million years old. These galaxies appear as tiny red smudges in images, their light stretched by the expansion of the universe from ultraviolet and visible wavelengths into the infrared. Some of them are surprisingly bright and massive, suggesting that galaxy formation occurred even earlier and more efficiently than some theories predicted. One of the remarkable features of these early galaxies is their star formation rates. Many of them were forming stars at prodigious rates, sometimes hundreds of times faster than the Milky Way does today. This makes sense in the context of the early universe. Gas was abundant, collisions and mergers were frequent, and the conditions were ripe for rapid star formation. These galaxies were building themselves up quickly, assembling their stellar populations in intense bursts of activity. As galaxies formed and grew, they also developed internal structure. Gas flowing into a galaxy would cool and settle into a rotating disk. Within that disk, dense regions would fragment and form stars. Over time, as more gas accreted and more stars formed, some galaxies developed distinct spiral arms, patterns created by density waves propagating through the disk. Other galaxies experienced major mergers, violent collisions that disrupted their structure, stirring their stars into more spheroidal distributions, forming elliptical galaxies. At the centres of these growing galaxies, something else was happening. Some of the gas flowing inward didn't form stars. Instead, it fell all the way to the centre, into the deepest part of the gravitational well. Here, it accumulated around the central black hole, a black hole that might have been seeded by a population through supermassive star, or formed from the collapse of a dense star cluster, or grown from smaller black holes that had merged. As gas spiraled into the black hole, it formed an accretion disk, a swirling maelstrom of superheated material. Friction in the disk heated the gas to millions of degrees, causing it to emit vast amounts of radiation, mostly in X-rays and ultraviolet light. In some cases, powerful magnetic fields channeled some of the infalling material into jets, narrow beams of particles and energy that shot outward at nearly the speed of light, perpendicular to the accretion disk. These active galactic nuclei, or AGN, could outshine their entire host galaxy, visible across billions of light-years. The most luminous AGN are called quasars, quasi-stellar objects, because they appeared point-like in early observations, like stars but were far too bright and too distant to be stars. Quasars are powered by supermassive black holes with millions to billions of times the mass of the Sun, accreting gas at extraordinary rates. The energy output of a quasar can exceed 10 to the 40 watts, more than 1 trillion times the luminosity of the Sun. Quasars were most common when the universe was between 1 and 3 billion years old, during a period of intense galaxy growth and merger activity. As we look back in time by observing more and more distant objects, we see more and more quasars. They mark an era when galaxies were young and active, when supermassive black holes were gorging on gas, when star formation was at its peak. Today, quasars are much rarer because most galaxies have settled into a more quiescent state, their central black holes having consumed most of the nearby gas, now starving and quiet. If you could somehow step outside the universe and look at it on the largest scales, you would see an astonishing structure. Galaxies aren't scattered randomly through space. Instead, they're arranged in an intricate network of filaments, sheets and knots, with vast empty regions, voids in between. This is the cosmic web, the large-scale structure of the universe, and it's one of the most striking features of the cosmos. The cosmic web grew from those tiny density fluctuations imprinted during inflation. As we've discussed, regions that were slightly denser than average attracted more matter under gravity, becoming even denser. Regions that were slightly less dense lost matter, becoming voids. But the pattern of these fluctuations wasn't random in the sense of being completely chaotic. It had structure, peaks and valleys in the density field, and this structure shaped how matter flowed. Dark matter, as always, led the way. It collapsed first, forming halos and filaments, the gravitational scaffolding of the universe. Ordinary matter followed, flowing along the gravitational gradients established by dark matter, like rivers flowing downhill, where multiple filaments intersected, where the gravitational potential was deepest. Matter accumulated in great concentrations. These became the sites of galaxy clusters, the largest gravitationally bound structures in the universe. By about 3 to 4 billion years after the Big Bang, the cosmic web had taken on its basic form. Simulations of cosmic structure formation, running on some of the world's most powerful supercomputers, can reproduce this structure with remarkable accuracy. You input the laws of gravity, the properties of dark matter, the initial conditions from inflation, and the simulation evolves forward in time. The result is a universe that looks, on large scales, very much like the one we observe. These simulations show dark matter forming a network of filaments, each one perhaps 10 to 100 million light-years long, stretching across the universe. The filaments are not uniform, they're lumpy, with denser nodes where filaments intersect. Ordinary matter, represented in the simulations as gas, flows into these dark matter structures. In the densest regions, the gas cools and forms galaxies. These galaxies then move along the filaments, sometimes colliding and merging, gradually building up larger and larger structures. The voids, the regions between the filaments, are not completely empty, but they're much less dense. They contain some galaxies, often smaller and more isolated ones, but the vast majority of the voids, the regions between the filaments, are not completely empty, but they're much less dense. They contain some galaxies, often smaller and more isolated ones, but the vast majority of matter avoids them. These voids can be enormous, spanning 200 million light-years or more across. Within them, space expands relatively unimpeded by gravity. In fact, voids are expanding faster than the average expansion rate of the universe because there's so little matter to slow them down. The cosmic web is visible in large galaxy surveys. Projects like the Sloan Digital Sky Survey have mapped the positions of millions of galaxies, creating three-dimensional maps of cosmic structure. When you plot these positions, the web becomes apparent. You see chains of galaxies, walls and sheets, all interconnected with dark voids between them. One of the most striking features discovered is the so-called Great Wall, a vast sheet-like structure of galaxies stretching across more than 500 million light-years. It's not a physical structure in the sense of being bound together, but rather a coherent feature in the distribution of galaxies. The largest structures in the cosmic web are galaxy clusters, collections of hundreds to thousands of galaxies bound together by their mutual gravity. The space between the galaxies in a cluster is filled with hot gas, heated to tens of millions of degrees by the gravitational energy of the cluster. This gas emits X-rays, making clusters bright in X-ray observations. The total mass of a cluster is dominated by dark matter, which typically comprises about 85% of the total. Ordinary matter in the form of stars and gas makes up most of the rest, though even this ordinary matter is mostly in the hot gas between galaxies rather than in the galaxies themselves. Galaxy clusters are still growing today through mergers and accretion. When two clusters collide, the process unfolds over hundreds of millions of years. The galaxies themselves mostly pass through each other. Stars are so far apart that collisions between individual stars are incredibly rare. But the hot gas in the clusters collides and shocks, heating to even higher temperatures, glowing brightly in X-rays. The dark matter halos also interact, not through direct collisions since dark matter doesn't interact electromagnetically, but through gravity. The clusters merge, eventually settling into a new equilibrium. One of the most famous cluster mergers is the Bullet cluster, so named because one cluster has passed through another, like a bullet through a target. Observations of the Bullet cluster provide some of the strongest evidence for dark matter. The hot gas in both clusters, visible in X-ray images, has been slowed down by the collision and remains behind. But the dark matter, which doesn't interact except through gravity, has passed right through, continuing onward with the galaxies. By measuring the gravitational lensing effect, the bending of light from background galaxies, astronomers can map where the mass is. And they find that most of the mass is with the galaxies, not with the gas. This separation of visible matter and mass is exactly what you'd expect if dark matter exists and doesn't interact electromagnetically. Filaments connecting clusters contain what's called the warm, hot intergalactic medium, or WIM. This is gas heated to temperatures of 100,000 to 10 million Kelvin, hot enough to be highly ionized, but often too cool to emit strong X-rays and too hot to absorb much visible light. For years, astronomers suspected that much of the ordinary matter in the universe was hiding in the WIM, too diffuse and at the wrong temperature to be easily detected. Recent observations, particularly with X-ray satellites and ultraviolet spectrographs, have started to detect this gas, confirming that a significant fraction of the baryonic matter in the universe resides in these filaments. The cosmic web is not static. It continues to evolve as the universe expands and ages. gravity continues to pull matter into the densest regions, making rich clusters richer and leaving voids emptier. But there's another force at play now, one that's changing the future trajectory of cosmic structure formation: dark energy. Dark energy is perhaps the most mysterious component of the universe. It appears to be a form of energy that fills all of space uniformly, causing the expansion of the universe to accelerate. Unlike matter, which attracts gravitationally and slows expansion, dark energy has a repulsive effect. The more the universe expands, the more dark energy there is because it has constant density even as space grows, and this drives ever faster expansion. Evidence for dark energy came from observations of distant supernovae in the late 1990s. Two teams, the Supernova Cosmology project and the High Z Supernova Search team, were measuring the distances and redshifts of Type Ia supernova, which serve as standard candles, objects with known intrinsic brightness. By comparing the apparent brightness to the known intrinsic brightness, you can calculate distance. By measuring redshift, you can determine how much the universe has expanded since the light was emitted. What they found was shocking. The distant supernovae were dimmer than expected, meaning they were farther away than calculations predicted. The only way to explain this was if the expansion of the universe had been accelerating. Something was pushing space apart, overcoming the attractive pull of gravity. This discovery earned the leaders of both teams, Saul Perlmutter, Brian Schmidt, and Adam Riess, the Nobel Prize in Physics in 2011. Dark energy now appears to comprise about 68% of the total energy density of the universe. Dark matter accounts for about 27%, and ordinary matter, everything made of atoms, makes up only about 5%. We live in a universe dominated by two things we don't understand: dark matter and dark energy, with the familiar world of stars, planets, and people representing just a tiny fraction of the whole. The presence of dark energy has profound implications for the future of cosmic structure formation. As dark energy drives accelerated expansion, it's becoming harder for gravity to pull structures together. Galaxy clusters that are not yet gravitationally bound will never collapse. They'll be swept apart by the expansion of space. Even structures that are currently forming will eventually stop growing. The universe is entering an era where large-scale structure formation is shutting down, frozen by the relentless push of dark energy. Between about 1 and 8 billion years after the Big Bang, the universe experienced its most active phase of galaxy evolution. This is sometimes called the epoch of galaxy assembly, or the cosmic noon, a period when star formation rates peaked, when galaxies were actively growing through mergers and gas accretion, when the universe was, in many ways, at its most vibrant. Galaxies come in a remarkable variety of shapes, sizes, and colours. The astronomer Edwin Hubble, working in the 1920s and 30s, developed a classification scheme that's still used today. He divided galaxies into several main types: elliptical, spiral, and irregular. Elliptical galaxies are smooth and featureless, shaped like ellipsoids, ranging from nearly spherical to highly elongated. They contain mostly old red stars and have little gas or dust, which means they're not forming many new stars. Ellipticals are typically found in dense environments like galaxy clusters, and they range in size from dwarf ellipticals containing millions of stars to giant ellipticals with trillions of stars. Spiral galaxies, like our own Milky Way, have a flat disk with spiral arms winding outward from a central bulge. The disk contains gas, dust, and both old and young stars, while the bulge and the surrounding halo contain mostly older stars. Spiral arms are not permanent structures, but density waves, regions where stars and gas bunch up temporarily as they orbit the galactic centre. These density waves trigger star formation, which is why spiral arms appear bright and blue, filled with young massive stars. Irregular galaxies lack a coherent structure. They're lumpy and chaotic, often small and rich in gas, undergoing active star formation. Many irregulars are the result of gravitational interactions or mergers with other galaxies, their structure disrupted by tidal forces. Hubble arranged these types in a sequence he called the Hubble tuning fork, with ellipticals on one side, spirals on the other, and a transition type called lenticular in between. Lenticular galaxies have a disk-like spirals, but no spiral arms and little ongoing star formation, resembling ellipticals in some ways and spirals in others. For decades, astronomers debated how galaxies formed and evolved. Did ellipticals form first and then spin up to create spirals? Or did spirals merge to create ellipticals? The answer, revealed through observations and simulations, is more nuanced. Galaxies evolve through a combination of processes: gas accretion, star formation, mergers, and interactions with their environment. In the early universe, galaxies were smaller and more irregular. They grew by accreting gas from their surroundings and by merging with other galaxies. When two spiral galaxies of similar size merge, the collision disrupts their disks, scattering stars and gas. The result is typically an elliptical galaxy, its stars moving on random orbits rather than in an organized disk. This merger process can also trigger intense star formation as gas clouds collide and compress, leading to what's called a starburst, where a galaxy forms stars at a rate far exceeding normal levels. Major mergers were common in the early universe, when galaxies were closer together and moving more slowly relative to each other. As the universe expanded and galaxies spread out, major mergers became less frequent. Today, in our local region of space, major mergers are relatively rare, though they still happen. The Milky Way and our neighbour, the Andromeda Galaxy, are currently approaching each other and will collide in about 4 billion years, eventually merging into a single, larger elliptical galaxy. Minor mergers, where a large galaxy absorbs a much smaller one, are more common. The Milky Way is currently in the process of cannibalizing several small dwarf galaxies, including the Sagittarius dwarf elliptical galaxy. These minor mergers add stars to the larger galaxy, but typically don't disrupt its overall structure significantly. Star formation in galaxies is not constant. It occurs in bursts triggered by various processes. Gas falling into a galaxy can compress existing gas, leading to star formation. Mergers and interactions can funnel gas toward the center of a galaxy, triggering a starburst. Density waves in spiral arms compress gas as they pass through, sparking new generations of stars. But star formation can also be shut down, a process called quenching. Several mechanisms can quench star formation. Active galactic nuclei, the supermassive black holes at galaxy centers, can produce powerful winds and jets that heat or eject gas from the galaxy, removing the raw material needed to form stars. Supernova explosions can also drive winds, pushing gas out of the galaxy. In dense environments like galaxy clusters, ram pressure stripping occurs when a galaxy moves through the hot intracluster gas, which acts like a headwind, blowing gas out of the galaxy. As a result of these processes, galaxies follow different evolutionary paths. Some, called blue galaxies, remain gas-rich and actively forming stars. They appear blue because young, hot, massive stars dominate their light. Others, called red galaxies, have exhausted or lost their gas supply and are no longer forming stars. They appear red because their light is dominated by older, cooler, lower mass stars. There's also a transition population called green valley galaxies, which are in the process of moving from active star formation to quiescence. The majority of massive galaxies today are red and quiescent, while lower mass galaxies tend to be blue and actively forming stars. This mass-dependent behavior is one of the key features of galaxy evolution and reflects the interplay between gas supply, star formation, and feedback processes. Supermassive black holes play a crucial but complex role in galaxy evolution. Nearly every large galaxy contains a supermassive black hole at its center, with a mass ranging from millions to billions of times the mass of the Sun. The mass of the black hole is tightly correlated with properties of the galaxy's central bulge, suggesting a deep connection between black hole growth and galaxy formation. When a supermassive black hole is actively accreting gas, it becomes an active galactic nucleus, emitting enormous amounts of energy. This energy can heat the surrounding gas, preventing it from cooling and forming stars. In this way, AGN feedback can regulate star formation, preventing galaxies from converting all their gas into stars too quickly. This feedback is thought to be crucial in explaining why the most massive galaxies are red and dead rather than blue and forming stars vigorously. The relationship between galaxies and their dark matter halos is also central to understanding galaxy evolution. Each galaxy sits within a dark matter halo, the invisible gravitational scaffolding that holds it together. The properties of the halo, particularly its mass and formation history, influence the galaxy's evolution. More massive halos can retain more gas against supernova-driven winds, allowing for more sustained star formation. They're also more likely to be involved in mergers which can both trigger star formation and quench it, depending on the circumstances. By about 8 to 9 billion years after the Big Bang, roughly the age when our solar system formed, the universe had settled into a more mature phase. Star formation rates had peaked and begun to decline. Most of the massive galaxies had assembled and were transitioning to quiescence. The cosmic web was fully formed, with galaxy clusters, filaments, and voids in place. Dark energy had begun to dominate the universe's energy density, and the expansion was starting to accelerate. Stars do not form in isolation. They're born in clusters, sometimes dozens or hundreds at a time. From the collapse of giant molecular clouds, vast regions of coal, dense gas and dust floating in the interstellar medium. These clouds are among the largest structures in galaxies, often hundreds of light years across and containing tens of thousands to millions of solar masses of material. Molecular clouds are mostly hydrogen, like everything else in the universe, but also contain helium and trace amounts of heavier elements. The term molecular refers to the fact that much of the hydrogen exists as molecular hydrogen rather than individual atoms. The clouds also contain dust, tiny grains of silicate, carbon, and ice, which play a crucial role in the chemistry and physics of star formation. Within a molecular cloud, gravity is always trying to make the cloud collapse. But several forces oppose collapse: thermal pressure from the gas's temperature, turbulence from random motions and supersonic flows, and magnetic fields threading through the cloud. For star formation to occur, gravity must overcome these opposing forces in at least some regions of the cloud. This can happen when the cloud becomes sufficiently dense and cold, or when it's disturbed by an external trigger. Triggers can include the shockwave from a nearby supernova, compression from a spiral density wave passing through the galactic disk, or collision with another cloud. Once a region begins to collapse, the process feeds on itself. As the gas compresses, its gravitational pull strengthens, causing faster collapse. The collapsing region fragments into smaller clumps due to instabilities and turbulence. Each clump continues to collapse independently, forming what's called a protostar. A protostar is a dense core of gas that's still accumulating material from its surroundings. It's not yet hot enough in its core for nuclear fusion, so it shines purely from gravitational energy as it contracts. Surrounding the protostar is a disk of material, the protoplanetary disk or circumstellar disk. This disk forms because the collapsing gas has some initial rotation, and conservation of angular momentum causes the material to spin faster as it falls inward, flattening into a disk perpendicular to the rotation axis. Think of a figure skater pulling in their arms and spinning faster. The protoplanetary disk is where planets form, and understanding this process is crucial to understanding how our solar system and potentially billions of other planetary systems came to be. Our solar system formed about 4.6 billion years ago from such a disk. We know this age with remarkable precision from radiometric dating of meteorites, ancient rocks that have survived largely unchanged since the earliest days. The parent molecular cloud that collapsed to form the Sun and its planets likely contained material from previous generations of stars. Supernova explosions had enriched the cloud with heavy elements, all the elements heavier than helium, which astronomers collectively call metals, even though most of them aren't metallic in the everyday sense. The young Sun formed at the centre of the disk, where the density and temperature were highest. As the protostellar core accumulated more and more mass, its internal temperature climbed. After perhaps a few 100,000 years, the core temperature reached about 10 million Kelvin, hot enough for hydrogen fusion to ignite. The Sun became a true star, entering what's called the main sequence, the long stable phase of stellar evolution, where it will remain for about 10 billion years total, of which it's currently about halfway through. Meanwhile, in the cooler regions of the disk further from the Sun, planets were beginning to form. The process started with dust grains, those microscopic particles of silicate, carbon and ice. These grains collided and stuck together through a combination of electrostatic forces and weak van der Waals forces, gradually building up larger and larger particles. From dust to pebbles, from pebbles to boulders, from boulders to planetesimals, objects kilometres in size. Once planetesimals formed, gravity became the dominant force. Larger planetesimals attracted smaller ones, growing through accretion. This process was competitive. The largest planetesimals in a region would tend to accumulate most of the mass, while smaller ones either got absorbed or were ejected through gravitational interactions. Over a few million to tens of millions of years, planetesimals coalesced into protoplanets, and protoplanets into planets. The structure of the solar system reflects the temperature gradient in the protoplanetary disk. Close to the Sun, it was hot enough that only materials with high boiling points could condense into solid form. Silicates and metals could form grains, but ices like water, methane, and ammonia remained gaseous. This is why the inner planets, Mercury, Venus, Earth, and Mars, are small and rocky. They're composed mostly of silicates and metal, with little volatile material. Beyond a certain distance from the Sun, roughly around the orbit of Jupiter, temperatures were cold enough for water ice to condense. This boundary is called the frost line or snow line. Beyond the frost line, planet-forming material was much more abundant because ices are common and water is one of the most abundant molecules in the universe. This allowed the outer planets to grow much larger. Jupiter and Saturn, the gas giants, formed massive solid cores of rock and ice, perhaps 10 to 20 times the mass of Earth. Once these cores reached this critical mass, they were able to gravitationally capture huge amounts of hydrogen and helium gas from the surrounding disk, swelling into the enormous planets we see today. Jupiter is over 300 times the mass of Earth, mostly hydrogen and helium with a relatively small core. Uranus and Neptune, the ice giants, formed further out where the disk was less dense. They were able to build up substantial cores of ice and rock, but didn't capture as much gas as Jupiter and Saturn before the disk dissipated. As a result, they're smaller and have a higher proportion of heavy elements relative to hydrogen and helium. The asteroid belt, located between Mars and Jupiter, is a region where planet formation was prevented by Jupiter's powerful gravity. Jupiter's gravitational influence stirred up the planetesimals in this region, causing them to collide at high speeds, which led to fragmentation rather than growth. What remains today is a population of small rocky bodies, the largest being Ceres, which is about 950 kilometers in diameter. Beyond Neptune lies the Kuiper Belt, a region of icy bodies including Pluto and thousands of other objects. Even further out is the Oort cloud, a vast spherical shell of icy bodies extending perhaps halfway to the nearest star. These distant regions are the source of comets, which occasionally fall into the inner solar system and put on spectacular shows as their ices vaporize near the Sun. Planet formation was a violent process. Computer simulations show that the final stages of terrestrial planet formation involved giant impacts between protoplanets. Earth itself is thought to have experienced a collision with a Mars-sized object called Theia about 4.5 billion years ago. This impact ejected a huge amount of material into orbit around Earth, which coalesced to form the Moon. Evidence for this giant impact hypothesis includes the Moon's composition, which is similar to Earth's mantle, and the Moon's relatively low density, suggesting it's depleted in iron compared to Earth. The young solar system was also chaotic due to migration of the giant planets. As planets form and interact with the remaining gas and planetesimals in the disk, they can exchange angular momentum and migrate inward or outward. Jupiter likely migrated inward somewhat, then reversed direction and migrated outward, in a process called the Grand Tack. Saturn, Uranus and Neptune also migrated, and this migration scattered planetesimals throughout the solar system. One consequence of this migration was the Late Heavy Bombardment, a period about 4.1 to 3.8 billion years ago when the inner solar system experienced a spike in impact rates. Evidence comes from the dating of lunar rocks brought back by the Apollo missions, which show a cluster of impact ages in this period. The bombardment may have been triggered by a gravitational resonance between Jupiter and Saturn that destabilized the orbits of small bodies in the outer solar system, sending them careening inward. Despite this violence, or perhaps because of it, the solar system eventually settled into a relatively stable configuration. The planets found orbits that could persist for billions of years. The terrestrial planets ended up in the inner system, rocky and warm. The giant planets settled in the outer system, cold and massive. And in the quiet period that followed, life emerged on at least one world, fundamentally changing its surface, atmosphere, and perhaps even its long-term fate. Our solar system is not unique. In the 1990s, astronomers began detecting planets around other stars, exoplanets. The first confirmed detection around a Sun-like star came in 1995 with the discovery of 51 Pegasi b, a Jupiter mass planet orbiting extremely close to its star, completing an orbit in just 4 days. This was shocking. Giant planets weren't supposed to form so close to their stars, but planet migration can move them there. Since then, thousands of exoplanets have been discovered, revealing an astonishing diversity. Hot Jupiters orbit close to their stars, baked by intense radiation. Super-Earths, planets more massive than Earth, but less massive than Neptune, are common, even though our solar system doesn't have one. Mini-Neptunes, ice giants smaller than Neptune, are also abundant, and there are planets in orbits that would be unstable in our solar system. Planets with extreme eccentricities, planets orbiting binary stars, planets around white dwarf remnants. The Kepler Space Telescope, which operated from 2009 to 2018, revolutionized exoplanet studies. By continuously monitoring the brightness of over 150,000 stars, it detected thousands of planets using the transit method, where a planet passes in front of its star and causes a slight dimming. Statistical analysis of Kepler's data suggests that there are more planets than stars in the Milky Way. Billions of planets, potentially billions of rocky planets in habitable zones around their stars, where liquid water could exist on the surface. The habitable zone, also called the Goldilocks zone, is the range of distances from a star where a planet receives just the right amount of energy, not too hot, not too cold, for liquid water to be stable on its surface. For a Sun-like star, this zone extends from about 0.9 to 1.5 astronomical units, with Earth comfortably inside. For cooler stars, the zone is closer. For hotter stars, it's farther out. The question of whether life exists elsewhere in the universe remains unanswered, but the discovery of so many exoplanets, many inhabitable zones, suggests that the conditions for life may be widespread. Whether life actually arises under those conditions, and whether it evolves into complex intelligent forms, are questions we're only beginning to explore. The universe, for all its grand scale and violent processes, has a remarkable property. It creates complexity. From the nearly perfect uniformity of the early universe emerged atoms, then molecules, then stars, galaxies, planets, and on at least one world, life. This progression from simplicity to complexity is one of the most profound features of cosmic evolution. Heavy elements, the building blocks of planets and life, are created inside stars. Stars spend most of their lives fusing hydrogen into helium in their cores, a process that releases energy and supports the star against gravitational collapse. But this is just the beginning of stellar nuclear synthesis. In massive stars, those above about 8 solar masses, the core eventually exhausts its hydrogen. The core contracts and heats up until it's hot enough to fuse helium into carbon and oxygen. Later, if the star is massive enough, carbon fuses into neon, sodium and magnesium. Neon fuses into oxygen and magnesium. Oxygen fuses into silicon and sulfur. And finally, silicon fuses into iron. Each successive fusion stage requires higher temperatures and releases less energy. Hydrogen fusion can sustain a star for billions of years. Helium fusion lasts a few 100 million years. Carbon fusion lasts a few thousand years. Silicon fusion lasts just a few days. The star is racing toward catastrophe, building up an onion-like structure with layers of different elements. Iron is the end of the line. Fusing iron doesn't release energy. It requires energy input. So when the core of a massive star becomes dominated by iron, nuclear fusion stops. The core is now supported only by electron degeneracy pressure, a quantum mechanical effect where electrons resist being squeezed too close together. But there's a limit to how much mass this pressure can support. About 1.4 solar masses, called the Chandrasekhar limit. If the iron core exceeds this limit, it collapses catastrophically. In less than a second, the core, about the size of Earth, implodes to a sphere perhaps 20 kilometers across, forming a neutron star, or, if the core is massive enough, a black hole. The implosion sends a shockwave rebounding outward through the star's outer layers, blasting them into space in a supernova explosion. Supernovae are among the most energetic events in the universe, briefly outshining their entire host galaxy. The explosion ejects all the elements that were created in the star's core, and also synthesizes even heavier elements through rapid neutron capture, called the R process. Elements like gold, platinum, uranium, and thorium are created in the extreme conditions of the supernova and its aftermath. Not all heavy elements come from supernovae. In recent years, astronomers have confirmed that neutron star mergers, collisions between two neutron stars orbiting each other, are major producers of heavy elements. When two neutron stars spiral together and merge, the conditions are even more extreme than in a supernova. Enormous amounts of neutron-rich material are ejected, and our process nucleosynthesis goes into overdrive, creating massive amounts of gold, platinum, and other heavy elements. The first confirmed observation of a neutron star merger came in August 2017, when gravitational wave detectors LIGO and Virgo detected the signal of two neutron stars colliding in a galaxy 130 million light-years away. Within seconds, telescopes around the world flew to the location and observed the explosion, called a kilonova. The light showed spectral features consistent with the R process elements, confirming that neutron star mergers are cosmic element factories. All of these elements created in stars and stellar explosions are scattered into space. They mix with the interstellar medium, enriching it. When new stars form from this enriched gas, they incorporate these heavy elements. Second and third generation stars have higher metallicity, more heavy elements than first generation stars. Planets forming around these stars inherit this enriched composition. Earth's composition reflects this cosmic history. The iron in your blood, the calcium in your bones, the carbon in your DNA, all were created in stars that exploded billions of years ago. We are, quite literally, made of stardust, a phrase popularized by astronomer Carl Sagan, but one that captures a profound truth. The conditions for life, at least life as we know it, depend on this enrichment process. Life on Earth is based on carbon chemistry and requires liquid water, along with a host of other elements: nitrogen, oxygen, phosphorus, sulfur, and trace amounts of metals. All of these, except hydrogen and helium, came from stars. Earth formed with a rich inventory of heavy elements. Its core is mostly iron and nickel, having differentiated under gravity early in the planet's history. Its mantle is silicate rock, rich in oxygen, silicon, magnesium, and iron. Its crust, especially the continental crust, is even more enriched in lighter elements like silicon, aluminum, sodium, and potassium. But Earth's surface would be barren without water. Where did Earth's water come from? This is still debated. Some may have been present in the planetesimals that built Earth, trapped in minerals, but much of it likely came from later impacts, delivered by comets and water-rich asteroids from the outer solar system. The late heavy bombardment may have played a role, pummeling Earth with icy bodies that melted and formed oceans. With water, a stable surface, and a protective atmosphere, Earth became habitable. The early atmosphere was very different from today's, likely dominated by nitrogen, carbon dioxide, water vapour, and perhaps methane, with little to no free oxygen. But it was thick enough to retain heat and protect the surface from harmful solar radiation. Life emerged on Earth surprisingly quickly. The oldest known rocks are about 4 billion years old, and they already contain hints of biological activity. By 3.5 billion years ago, fossil evidence clearly shows microbial life. These early organisms were simple, single-celled, prokaryotic bacteria and archaea. They lived in the oceans, possibly near hydrothermal vents where chemical energy was abundant. For more than 2 billion years, life remained microbial, but microbes were quietly reshaping the planet. Around 2.4 billion years ago, cyanobacteria evolved oxygenic photosynthesis, the ability to use sunlight to split water molecules and release oxygen as a byproduct. Initially, this oxygen was absorbed by oceans and rocks, oxidizing dissolved iron and creating banded iron formations. But eventually, oxygen began accumulating in the atmosphere, causing what's called the Great Oxidation Event. Oxygen was toxic to many anaerobic organisms, so this was a crisis, one of Earth's first major extinction events. But it also opened new possibilities. Oxygen allows for aerobic respiration, a much more efficient way to extract energy from organic molecules. This set the stage for the evolution of more complex life. Around 2 billion years ago, eukaryotic cells appeared, larger and more complex than prokaryotes, with nuclei and specialized organelles. Eukaryotes likely arose through symbiosis, when one cell engulfed another, and instead of digesting it, formed a partnership. Mitochondria, the energy-producing organelles in eukaryotic cells, were once free-living bacteria. Chloroplasts in plant cells were once cyanobacteria. Multicellular life emerged around 1.5 to 1 billion years ago, initially simple algae and fungi. By around 600 million years ago, more complex multicellular organisms appeared, including the earliest animals. The Ediacaran period saw strange soft-bodied creatures, unlike anything alive today, preserved in rare fossil sites. Then came the Cambrian explosion, about 540 million years ago, when animal diversity skyrocketed. Most of the major animal groups, or phyla, that exist today appeared within a geologically brief period. The causes are still debated, but likely involve rising oxygen levels, ecological interactions, and evolutionary innovations like hard shells and predation. Life's subsequent history on Earth is marked by innovations and catastrophes. Plants colonized land around 450 million years ago, followed by animals. Forests arose, insects diversified, and vertebrates evolved from fish-like ancestors into amphibians, reptiles, mammals, and birds. 5 major mass extinctions punctuated this history, each wiping out large fractions of species but also opening ecological niches for survivors to exploit. The most recent mass extinction, 66 million years ago, was caused by an asteroid impact in what's now Mexico. The impact threw up enormous amounts of debris, blocking sunlight and causing a global winter. The dinosaurs, except for birds, went extinct. But mammals, small and adaptable, survived and diversified. Within 10 million years, mammals had evolved into a bewildering variety of forms, from whales to bats to primates. Humans evolved relatively recently, in cosmic terms. Our species, Homo sapiens, arose in Africa around 300,000 years ago. For most of our history, we lived as hunter-gatherers in small groups. Agriculture developed about 12,000 years ago, allowing for larger, settled populations. Civilizations arose. Writing was invented. Science and technology advanced. And now, here we are, a species capable of looking back across nearly 14 billion years of cosmic history, able to piece together the story of how we came to be. It's a remarkable journey from quantum fluctuations in the early universe to atoms, stars, galaxies, planets, and ultimately to conscious beings capable of understanding it all. For most of cosmic history, the expansion of the universe was slowing down. Gravity, pulling on all the matter in the universe, acted as a brake, decelerating the expansion. The question cosmologists asked in the 20th century was whether there was enough matter to eventually halt the expansion and cause the universe to recollapse in a big crunch, or whether it would expand forever, gradually diluting and cooling into a cold, empty void. Measurements of the universe's matter density suggested it was close to critical, the boundary between these two fates, but most evidence pointed toward eternal expansion. The universe seemed destined to grow ever larger, ever colder, ever more sparse. Then came the supernova observations in the late 1990s. As discussed earlier, 2 independent teams measured the distances and redshifts of distant Type Ia supernova and found that they were farther away than expected. The expansion of the universe wasn't slowing down, it was speeding up. This was a paradigm shift. Acceleration requires something with repulsive gravity, something that pushes space apart rather than pulling it together. The simplest explanation, and the one most consistent with observations, is the cosmological constant, a term that Einstein had introduced into his equations of general relativity nearly a century earlier. Einstein added the cosmological constant to his equations in 1917 because he wanted a static universe, one that neither expanded nor contracted. The constant, denoted by the Greek letter lambda, represents a uniform energy density inherent to space itself, a vacuum energy. With the right value, it could balance the attractive pull of matter and keep the universe static. But when Hubble discovered in 1929 that the universe was expanding, the need for a static model disappeared. Einstein reportedly called the cosmological constant his greatest blunder. For decades it was largely forgotten or set to zero in cosmological models. The supernova observations brought it roaring back. If you assume a cosmological constant, a uniform dark energy filling all of space with constant density, you can explain the accelerated expansion. And not only that, but you can explain several other observations that had puzzled cosmologists. The age of the universe, calculated from the expansion rate, had seemed uncomfortably young, younger than some of the oldest stars. With dark energy, the expansion history changes. The universe is older, about 13.8 billion years, comfortably older than any known stars. The geometry of the universe also makes more sense with dark energy. Observations of the cosmic microwave background indicated that space is flat, or very nearly so. But measurements of matter density suggested there wasn't enough matter to make the universe flat. Dark energy fills the gap. When you add up ordinary matter, and dark energy, the total energy density equals the critical density, making the universe geometrically flat, exactly as observed. Dark energy, if it exists as a cosmological constant, has some very peculiar properties. Unlike matter or radiation, its density doesn't dilute as the universe expands. Imagine a box containing some amount of dark energy. If you double the volume of the box, matter would spread out, and its density would drop by half. Radiation would do the same, plus lose energy due to redshifting. But dark energy would simply double in total amount, keeping its density constant. This might sound like it violates conservation of energy, but general relativity doesn't have a simple, global conservation of energy law when space itself is expanding. Energy can effectively be created or destroyed, depending on how you define your terms. What matters for the expansion is the energy density and pressure, and dark energy has a very specific relationship between these two: negative pressure. Pressure, in the context of cosmology, isn't just about pushing on the walls of a container. It relates to how a substance responds to expansion. Positive pressure, like that of gas, resists expansion. Negative pressure does the opposite. It drives expansion. Dark energy, if it's a cosmological constant, has a pressure equal to minus its energy density. This negative pressure creates a repulsive gravitational effect, causing space to expand faster over time. The evidence for dark energy now comes from multiple independent sources. In addition to distant supernova, astronomers study the large-scale structure of the universe, the distribution of galaxies and galaxy clusters. The pattern of structure depends on cosmic expansion history. With dark energy, structures grow differently than without it. Observations match the predictions of a universe with dark energy. Measurements of the cosmic microwave background also support dark energy. The detailed pattern of hot and cold spots in the CMB, depends on the geometry of the universe and its expansion history. The data from satellites like WMAP and Planck are exquisitely consistent with a flat universe dominated by dark energy. Gravitational lensing provides yet another test. Massive objects like galaxy clusters bend light from more distant objects, an effect predicted by general relativity. By carefully mapping this lensing, astronomers can measure the distribution of mass in the universe and infer the expansion history. Again, the results point to dark energy. But what is dark energy, really? The cosmological constant is one possibility, representing a fundamental property of empty space, a vacuum energy that's always been there and always will be. But there are other candidates. Some theories propose that dark energy is a new field, similar to the inflaton field that drove cosmic inflation, called quintessence. Unlike the cosmological constant, quintessence can vary in space and time. Its energy density might change as the universe evolves, leading to different predictions for the future. Another possibility is that we don't need dark energy at all, but rather need to modify our understanding of gravity. General relativity works extremely well on solar system scales and has passed every test we've thrown at it. But perhaps on cosmic scales, the larger scales in the universe, gravity behaves differently. Modified gravity theories have been proposed, but so far none have matched the full range of observations, as well as dark energy combined with general relativity. The nature of dark energy is one of the biggest unsolved problems in physics. Theorists have tried to calculate the vacuum energy from quantum field theory, summing up the zero-point energies of all quantum fields. The result they get is catastrophically wrong, larger than the observed dark energy density by a factor of 10 to the 120 power. This is sometimes called the worst prediction in the history of physics. Clearly, something is missing from our understanding. Perhaps there's a symmetry or mechanism that cancels most of the vacuum energy, leaving just the tiny amount we observe. Perhaps dark energy is telling us about quantum gravity, or extra dimensions, or physics beyond the standard model. We don't know. What we do know is that dark energy is shaping the future of the universe. As time goes on, dark energy becomes increasingly dominant. Already, it comprises about 68% of the universe's total energy density. As the universe continues to expand, matter will dilute further, but dark energy will maintain its density, making it even more dominant. This has consequences for cosmic structure formation, as mentioned earlier. Gravity is losing the battle. Regions that are not already gravitationally bound will never collapse. The cosmic web will stop evolving on the larger scales. Galaxy clusters that are bound will remain so, but they'll become increasingly isolated as the space between them expands faster and faster. Eventually, billions of years from now, galaxies outside our local group will recede beyond what's called the cosmic horizon, the distance beyond which light can never reach us because space is expanding faster than light can travel through it. These galaxies will disappear from view, redshifted into invisibility. Future astronomers in the far distant future, if any exist, might look out and see only their local group of galaxies surrounded by darkness, with no evidence of the larger cosmos. The ultimate fate of the universe depends on the exact nature of dark energy. If it's a cosmological constant, the universe will continue expanding forever, accelerating without bound. The Big Freeze scenario, also called heat death, envisions a universe that grows ever colder, ever darker, ever emptier. Stars will exhaust their fuel and die. Galaxies will go dark. Black holes will evaporate through Hawking radiation over unimaginably long timescales, perhaps 10 to the 100 power years. Eventually, nothing will remain but a dilute sea of particles and radiation, approaching absolute zero, a universe in thermodynamic equilibrium, silent and still. If dark energy is quintessence, and its density increases over time, the universe could end in a big rip. In this scenario, the accelerated expansion becomes so extreme that it eventually tears apart gravitationally bound structures. First, galaxy clusters would be ripped apart, then galaxies, then stellar systems, then planets, then atoms, and finally even atomic nuclei and subatomic particles. The universe would be shredded down to its fundamental components, space-time itself perhaps disintegrating in the final moments. Alternatively, if dark energy weakens or reverses, the expansion could slow or even turn into contraction, leading to a big crunch where the universe collapses back on itself, ending in a hot, dense state similar to the Big Bang. Some cyclic models propose that the universe undergoes an endless series of expansions and contractions, big bangs followed by big crunches, each cycle potentially spawning a new universe with different physical constants. These are speculations informed by physics and observation, but reaching far into an uncertain future. What we can say with confidence is that the universe's expansion is accelerating now, driven by something we call dark energy, and that this acceleration will profoundly shape the cosmos for eons to come. Let's pause now and take stock. Here we are, 13.8 billion years after the Big Bang, living on a rocky planet orbiting an ordinary star in an ordinary galaxy, looking outward at a universe vast beyond comprehension. The observable universe is the region of space from which light has had time to reach us since the Big Bang. This doesn't mean we can see 13.8 billion light years in every direction. The universe has been expanding while light travels, so the most distant objects we can see are now much farther away than 13.8 billion light years. The radius of the observable universe is about 46 billion light years. This might seem like it violates the speed of light limit. How can something be 46 billion light years away if the universe is only 13.8 billion years old? The answer is that space itself has been expanding. An object that emitted light shortly after the Big Bang has been carried away by cosmic expansion while its light was travelling toward us. By the time the light reaches us, that object is now far more distant than it was when the light was emitted. The observable universe contains an almost incomprehensible amount of structure. Current estimates suggest there are about 200 billion to 2 trillion galaxies in the observable universe. Each galaxy contains, on average, hundreds of billions of stars. So the total number of stars is around 10 to the 24th power, a trillion. And around many of those stars, planets orbit. The number of planets could easily exceed the number of stars. Looking outward from Earth, we see the universe arranged in a hierarchy of structures. Our Sun is one of perhaps 400 billion stars in the Milky Way galaxy. The Milky Way is a large spiral galaxy about 100,000 light-years across, with a prominent central bulge and several spiral arms. We're located in the Orion Arm, about 27,000 light-years from the galactic centre. The Milky Way is not alone. It's part of what's called the Local Group, a collection of about 80 galaxies spread across a region roughly 10 million light-years in diameter. The Local Group's two dominant members are the Milky Way and the Andromeda Galaxy, also called M31. Andromeda is slightly larger than the Milky Way and is approaching us at about 110 kilometers per second. In about 4 billion years, the two galaxies will collide and merge. The Local Group also contains dozens of smaller galaxies, including the Triangulum Galaxy, and numerous dwarf galaxies orbiting the Milky Way and Andromeda. The large and small Magellanic Clouds, visible from the southern hemisphere, are dwarf galaxies orbiting the Milky Way. They're being tidally distorted by the Milky Way's gravity, and streams of gas have been pulled out of them, forming structures like the Magellanic Stream. The local group, in turn, is part of the Virgo supercluster, an enormous structure containing thousands of galaxies spread across about 110 million light-years. The Virgo cluster, near the heart of the supercluster, is a massive concentration of over 1,000 galaxies dominated by the giant elliptical M87, which harbours a supermassive black hole 6 billion times the mass of the Sun. This is the black hole famously imaged by the Event Horizon Telescope in 2019, showing the shadow of the event horizon surrounded by a glowing accretion disk. But even the Virgo supercluster is just one part of a larger structure called Laniakea, a Hawaiian word meaning immeasurable heaven. Laniakea is a supercluster of superclusters containing about 100,000 galaxies spread across 520 million light-years. It's defined not just by the positions of galaxies, but by their motions. Galaxies throughout Laniakea are slowly moving toward the structure's centre of mass, a region called the Great Attractor. The Great Attractor itself is a massive concentration of mass partially obscured by the plane of the Milky Way, making it difficult to observe directly. But its gravitational influence is unmistakable, pulling on thousands of galaxies, including our own. Beyond the Great Attractor lies an even larger mass concentration called the Shapley supercluster, which is also exerting a gravitational pull on our local region of space. When we map the universe on the largest scales, plotting the positions of millions of galaxies, we see the cosmic web in all its glory. Filaments of galaxies stretch across hundreds of millions of light-years. Walls and sheets of galaxies form surfaces in three-dimensional space, and voids, the great empty regions, dominate the volume. About 80% of the universe's volume is in voids, with galaxies concentrated in the remaining 20% along filaments and walls and in dense clusters. One of the largest known structures in the universe is the Hercules Corona Borealis Great Wall, a filament or wall of galaxy clusters stretching across about 10 billion light-years. Structures this large are near the upper limit of what's expected in standard cosmological models. They formed from the gravitational collapse of density fluctuations, but there's only been 13.8 billion years for gravity to act. Larger structures simply wouldn't have had time to form. When we look at the most distant objects visible, we're seeing the universe as it was billions of years ago, because light from those objects has taken billions of years to reach us. The most distant individual galaxy confirmed so far, as of late 2024, is JD's GS Z14-0, observed by the James Webb Space Telescope. Its light was emitted when the universe was only about 290 million years old. We're seeing this galaxy as it was in its infancy, a small irregular collection of young hot stars. Beyond the most distant galaxies lies the cosmic microwave background, the most distant thing we can observe. The CMB marks the surface of last scattering, the moment when photons decoupled from matter and began streaming freely through space. This light was emitted when the universe was 370,000 years old, and it comes from every direction. Looking at the CMB is like looking at a spherical shell surrounding us, centered on Earth, but not because we're special. Any observer anywhere in the universe would see their own CMB shell, centered on their location. Beyond the CMB, the universe is opaque. We cannot see directly to earlier times using light, but we can infer what was happening from the CMB's properties, from the abundances of light elements created in Big Bang nuclear synthesis, from gravitational wave observations, and from theoretical physics. The observable universe has a boundary, the cosmic horizon, but this boundary is not an edge in space. It's a horizon in time, Light from beyond this distance simply hasn't had time to reach us yet. And because the universe is expanding and accelerating, there are regions of space whose light will never reach us, no matter how long we wait. They're receding faster than light can catch up. This means there's likely much more universe beyond what we can observe. The universe could be infinite, extending far beyond our horizon, with more galaxies, more stars, more planets stretching on forever. Or it could be finite but unbound, curving back on itself like the surface of a higher dimensional sphere. We don't know which is true. Current observations suggest the universe is flat, or very close to it, which could mean it's infinite, but there's still some uncertainty. Within the observable universe, the composition is now well established. About 68% of the total energy density is dark energy. About 27% is dark matter. About 5% is ordinary matter, the stuff we're made of. But even this ordinary matter is mostly not in stars. Stars comprise only about 0.5% of the total. Most ordinary matter is in diffuse gas, the warm, hot intergalactic medium threading through filaments, and the hot gas in galaxy clusters. The universe is filled with light, the cosmic microwave background radiation bathing everything in a faint glow of microwaves. But there's also the cosmic infrared background from all the stars and galaxies that have ever formed, their light stretched into the infrared by cosmic expansion. There's the cosmic ultraviolet background from hot stars and quasars. There are cosmic rays, high-energy particles accelerated by supernovae and other violent events, streaming through space at nearly the speed of light. And there's the cosmic neutrino background, a sea of neutrinos left over from 1 second after the Big Bang, now cooled to about 2 Kelvin. These neutrinos have never been directly detected, but they're predicted to fill the universe at a density of about 300 per cubic centimetre. Everywhere you go, billions of neutrinos pass through your body every second, barely interacting with anything. The universe today is a busy, dynamic place. Stars are still forming in galaxies, though at a much lower rate than during cosmic noon. Supernovae explode roughly once per second somewhere in the observable universe. Black holes merge, sending ripples of gravitational waves across space-time. Comets and asteroids collide with planets. Life, at least on Earth, continues to evolve and adapt. And somewhere in all this vastness, on an unremarkable planet orbiting an unremarkable star, conscious beings have emerged, capable of looking outward and asking questions. How did we get here? What is our place in the cosmos? What does the future hold? These questions drive science forward, pushing us to explore, to discover, to understand. We've come a long way from the early days when we thought Earth was the centre of everything. We now know we're on one planet among many, orbiting one star among hundreds of billions, in one galaxy among trillions, in a universe so vast it challenges comprehension. And yet, for all its scale, the universe follows rules. Mathematics describes its behaviour, physics predicts its evolution, observations confirm or refute our theories. The universe is knowable, at least in part, and that's perhaps the most remarkable thing of all. Let's come to rest now. Here at the end of our journey, we've travelled from the very first instant, from the Planck epoch through inflation and nucleosynthesis, through the dark ages to the first stars, through billions of years of cosmic evolution to the universe we inhabit today. It's been quite a voyage, spanning nearly 14 billion years and 46 billion light years. Think about it for a moment. Everything around you, every atom in your body, has a history that stretches back to the Big Bang. The hydrogen atoms in your water molecules were created in the first 3 minutes. The carbon, nitrogen, and oxygen that make up your cells were forged in the cores of ancient stars that exploded as supernovae long before the sun was born. The iron in your blood might have come from a white dwarf star that went supernova, or from the core of a massive star in its death throes. You are made of star stuff, but you're also made of space-time itself, of quantum fields vibrating in patterns complex enough to be aware, to wonder, to ask questions about your own origins. The universe through you is contemplating itself. This story we've told tonight is not complete. There are gaps in our understanding, questions we cannot yet answer. What happened before the Big Bang? Or does that question even make sense? What is dark matter made of? What is the true nature of dark energy? Are we alone in the universe, or is life common? What lies beyond the edge of the observable universe? These unknowns are not failures of science. They're invitations. They remind us that for all we've learned, there's still so much more to discover. Each answer we find leads to new questions, deeper mysteries. The universe continues to surprise us, to challenge our assumptions, to reveal layers of complexity and beauty we never imagined. And perhaps that's fitting. We're part of this universe after all, not separate from it. We're participants in an ongoing story of cosmic evolution. The same forces that shaped galaxies have shaped our world, our species, our minds. We're the universe waking up, looking around and beginning to understand where it came from and where it might be going. As you drift off to sleep tonight, let yourself feel that connection. You're not just in the universe. You are the universe, a small part of it perhaps, but a part nonetheless. The atoms flowing through your veins right now have been on an incredible journey, through stellar cores and supernova explosions, through interstellar clouds and protoplanetary disks, through billions of years of cosmic history, all to be here, now, in this moment, in you. The story of the observable universe is also your story. It's everyone's story. From quantum fluctuations in the inflaton field to conscious beings reading books and watching stars, it's all one continuous thread, woven through time and space, connecting everything to everything else. So rest now. Let the vastness wash over you, not as something frightening or overwhelming, but as something wondrous. You're safe here, on this small blue world, spinning through space, held in the gentle grip of gravity, sheltered by an atmosphere, warmed by a star. And when you wake tomorrow, the universe will still be here, still expanding, still evolving, still creating new structures and new possibilities. The story continues, and you get to be part of it. Thank you for joining me on this journey through cosmic time. If you've enjoyed drifting through the history of the observable universe, and if these sleepy explorations bring you some peace, I'd be grateful if you'd consider subscribing. Your support helps this channel continue exploring the wonders of science and the cosmos, one gentle narration at a time. And if you have suggestions for future topics you'd like to explore, drop them in the comments. I read everyone. Until next time, sleep well. Dream of stars and galaxies, of time and space, of the extraordinary universe we're fortunate enough to call home. Good night.